What is a number?
A number is an abstract way to represent a quantity.
That's a very good answer.
I just thought of that.
It's a very good answer. I spent, I think, most of my PhD years thinking about the answer to that, and that's more or less what I had.
You should have given me a call. I would have told you. All right.
You're a hard man to reach.
All right. Okay, good answer. Okay, are we right? What is a number?
Right. So, as you said, it's just an abstract thing that represents quantity. Now, if you ask somebody, they might tell you, by giving examples. So, what is a number? Well, 0 is a number, 1 is a number, 42 is certainly a number. Okay. What about half? Oh, okay, half is a number. Minus 3 over 8 is a number. Wait, what about the square root of 2? Oh, that's also a number. What about pi? What about e? All of these things are numbers. What about I? What about the square root of minus 1? Right. Oh, that's imaginary. That's not a real number. So I is also a number, right? It's just not one that makes sense to you sort of as a human. But in electric engineering, they use I to talk about electricity flow and stuff like this. So I is also a number. You can use other things as numbers, right? But that still doesn't really answer, mathematically speaking, what's a number. Now, I'm going to give it away. I don't have an answer to that. There is no answer to that. But what can a number be? So, for example, a number, if you want to have a strict foundation of mathematics, you want to say, I'm going to start with one thing and build math on that. This is going to be a bit controversial, but the de facto standard nowadays is set theory with the Zermelo-Fraenkel axioms, or ZFC, with the axiom of choice. We're not going to go into, oh, that's the only one. It's not the only one. There's a lot of different ones. But ZFC is one of the main foundations of modern mathematics. First of all, what is a set?
Yep.
A set is a collection of mathematical objects, right? These could be numbers or other sets and so on. In set theory, everything is a set. So if you think about numbers, you're thinking about sets. Now that sounds odd for a lot of people because you're not used to this, but if you think about computers, then a letter is a number. A picture file is also a number. So all of these things are represented using other things. It's just a matter of coding stuff into a system. So a lot of times you will see something that says, so let's say that the number 0 is the empty set. So this is the set that has no elements, nothing in it. Think about an empty bag. Let's say that we already have defined the number n. So the next one is just going to be whatever n was defined, and we add to it n itself. So 1 is going to be just 0, which is just the empty set, and 2 is going to be 0 and 1, right? Because we add 0 and we add 1 itself, which is empty set, and this. So what would 3 be? Well, 0, 1, 2, and this just goes on. So in effect, a number is just 0 all the way to n minus 1.
So why is 1 the empty set? I thought 0 was the empty set.
So this is the set whose element is the empty set. So it's a bag containing nothing.
Okay.
Right.
So all numbers are just bags of nothing. It's just how many nothings have you got?
Kind of. But now we get tricky. So this is just the natural number. So 0, 1, whatever. What's half? What's minus 1? Right. All of these things are not represented here. So now you can start, let's call it going a bit crazy with this. And you can say, okay, I'm going to define a collection of natural numbers and say this one represents, minus 1. And another collection that represents minus 2 and so on and so on. And then you can take those and use this to represent the fractions. And then you can use all kind of constructions to go from there and get the real number. So for example, after I defined all the natural numbers, let's call this n, how do I get to z, which is the integer? So this is also minus 1, minus 2, minus 3, and so on. Just for clarity, 0 is a natural number. This is also a very contentious point. So it is.
All right.
Let's just clarify that.
I'll put your email address down there.
How do we get from here to here? Well, for example, so you want to get from the natural numbers to the integers. So one way to think about this is to sort of think about pairs of numbers. So I have a pair, let's call them x and y, and another pair, let's call this x prime and y prime. And I want to think that they represent the same thing if x plus y prime is x prime plus y. So, for example, let's put in 0 and 1. This would be x and y, and this would be 3 and 4. Let's see if I was right. That's 0 plus 4 equals 3 plus 1. So this is 4. So I was right. Everything works. These two things are kind of the same. So let me, put this approximate, not exactly equal.
Okay.
Right. And you can use this now to say, okay, let's look at all of these pairs of numbers that have this kind of thing. And let's call all of these minus 1. So minus 1 is now really just all the pairs of numbers, x, y, such that 0, 1 is the same as x, y. And now I can extend the addition from the natural numbers to this. So minus 2 would be xy, such that 0, 2 is the same as xy under this weak equality. That gives you a way to define minus 1 and so on. But you can also redefine 0. So 0 is now xy, where 0, 0 equals this xy, which if you think about this, just means that x equals y. So that's 0, but hang on, 0 is the empty set. And now I'm saying it's not the empty set. It's this collection of pairs. And here's the important thing. It's just coding. You just have to decide how you code your numbers. Right? So you can say, okay, I'm starting from this. I'm building the system up. And then at the end, so from this you can continue and define the rational numbers, the real numbers, the complex numbers, whatever. And then you can say, let me end this at the complex numbers, right? So I went from this to the rational numbers, so half, minus 3/8, whatever, and from here to the real numbers with pi and the square root of 2, and from here to the complex numbers with I and whatever. So I can say, okay, let me define all of these number systems, and each of those has sort of a canonical way that the previous one mapped into that. So now I have a canonical way of putting the natural numbers into the complex numbers. So the empty set is now, moved here to this particular set, and then to that particular set, whatever I end up here, moved to this particular set, moved to that particular set. Now I can decide that the natural numbers are not this thing, they're actually whatever I ended up with as the copy in this one. So what's a number from a mathematical, let's say, objective reality? It's whatever you want it to be.
Like a really popular question that everyone always asks on the internet is, do numbers exist, or were numbers invented, or do they just exist in the world? Presumably you think numbers are very much a human invention.
Well, philosophically speaking, I'm very agnostic. I don't want to have any concrete set of beliefs, because beliefs lead you to being sure that you're right, and you can't really know. The point here is that numbers exist within a context. And if you're thinking about set theory as your context, then numbers are whatever you decide to mean, whatever you decide that numbers mean in this context, whatever coding you want. Do you want the standard coding for the natural numbers? Do you want to go into the complex numbers? You can use different sets. You can use the empty set to say, I want the empty set to be 5, and I want 0 to be some other set. It's fine. Right? It's all about coding. And the important thing, and this is where ZFC as a set theory has a lot of power, is that it just shows that whatever coding you did, if it satisfies the basic properties that you think of for the natural numbers, it doesn't matter. You can always translate this to that and vice versa. So it's like if you have something written in ASCII and something written in Unicode, you can just move between those two let's say in English without all the emoji symbols, right? So you can just move between those two encodings, and that's fine.
Could mathematics, modern thought exist without numbers? Like, were numbers necessary, or was it just one of the paths we could have taken to reach where we are now?
It's a good and interesting question. I don't know, but they're so natural. But here's something that people forget. Sets are also as natural. People like to say, oh, numbers started when, like caveman was hunting a mammoth and was like, okay, there are 2 mammoths and there are 2 of us, so it's the same quantity. But to understand that there are 2 mammoths, you need to understand the collection of mammoths. And that's the basic of set theory, right? So the basic is not just numbers, it's numbers and sets, or arguably numbers and types, or numbers in some sort of, collections. And it's just so natural. I don't see how we could have gone without coming up with numbers.